Let's continue the discussion on this homework with problem number 21. Problem number 21 states, every few years the winds from Boulder, Colorado attain a sustained speed of 45 meters per second, about 100 miles per hour, when the jet stream descends during early spring. Approximately what is the force due to the Bernoulli effect on the roof having an area of 220 meters squared? Typical air density in Boulder is 1.14 kilograms per meter cubed, and the corresponding atmospheric pressure is 8.89 times 10 to the fourth newtons per square meter. Bernoulli's principle, as stated in the text, assumes laminar flow. Using the principles here produces only an approximate result because there is significant turbulence. Okay, so we have a velocity of 45 meters per second squared and an area of 220 square meters. And we're given rho is equal to 1.14 kilograms per meter cubed, and pressure is equal to 8.89 times 10 to the fourth newtons per square meter. And so we write Bernoulli's equation down, and I'm going to leave out the last part of it because, again, the height doesn't change, so I'm going to leave out the rho GH here because it would cancel out. And what happens is that one velocity is equal to 0 and the other velocity is equal to what we have up here. And so the difference in pressures is equal to 1/2 rho V2 squared. And that's because this cancels out. And so we have the difference in pressure. So the force is going to equal to the difference in pressures times the area. So force on the roof is going to equal to the area times the difference in pressure. And so that's going to equal to 220 times 1/2 rho V2 squared, which is going to equal 220 times 1/2 times 1.14 times V squared would be 45 squared. And if you multiply that out, it's going to be 2.54 times 10 to the fifth newtons. So that's the force on the roof. Number 22 says calculate the approximate force per square meter on a sail given a horizontal velocity of the wind on one side of the sail is 6 meters per second. On the other side of the sail, it's 3.5 meters per second. The density of the air is given, and this calculation shows the effect. And then it gives another question. It says, discuss whether this force is great enough to effectively propel the boat. So first, let's do the calculation. We have V1, which is on the one side, is 6, and V2 on the other side is 3.50. And we have rho is equal to 1.29. Again, with Bernoulli's equation, we don't need to have the rho GH because it's not part of the situation. So P1 plus 1/2 rho V1 squared is going to equal to P2 plus 1/2 rho V2 squared. And so again, the difference in pressure, which is what will propel the boat, is going to equal 1/2 rho times V2 minus, or V1 minus V2. And you can call 1 and 2 whatever you want, but it's going to equal to 1/2 times 1.29 times 6 squared. Sorry, there's a squared in here, I keep forgetting. Minus 3.50 squared. And when you work this out, you get 15.2 newtons per square meter, which doesn't seem like a whole lot, which is why, and this answers the second question, you have a small force, but generally sails have a fairly large, make up for that with a fairly large area. And so your total propelling force is going to be the multiplication of these two. And that's what leads to the motion of the boat. Number 23. What is the pressure drop due to Bernoulli's effect as water goes into a 3 centimeter nozzle from a 9 centimeter fire hose while carrying water at a flow rate of 40 liters per second? And then the second part is, what is the maximum height that the nozzle will rise? Okay, so the first question, we again use Bernoulli's equation, and for the first part, we're going to assume that for the first part, we're going to assume there's no change in height. So we have P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. And that means that P1 minus P2 is going to equal to 1/2 rho V1 minus V2 squared, the quantity squared. And so that's going to equal 1/2 times, now 1 times 10 to the third is the rho for water. And we're going to go from the flow rate is 40 times 10 to the minus 3, that's 40 liters per second, divided by, the velocity here is going to be that divided by the area, and the area is pi times r squared. And so it's going to be 40 times 10 to the minus 3 divided by pi times r squared here as well. So the radius is squared for the area. This is flow, this is Q over A in both these cases. And this is Q just expressed as meters cubed instead of liters. And so when you do this and work out the math, you get 1.56 times 10 to the, 5/8 times 10 to the 6th newtons per meter squared. So that's the difference. And one of these is 0. When it exits the nozzle, it's equal to 0, which would be P2 actually, not P1. And so P1 is going to equal this. And that's the first part. The pressure drop is going to be this minus 0. And so this is the pressure drop when it exits. It starts out at this pressure and drops to 0. Now the second part of this asks for the height. Now you have to introduce that new term. So you have P1 plus 1/2 rho V1 squared is plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho g H2. And we want H2 here. This is canceled out because when it reaches its maximum height, V is equal to 0. Okay? This and this are also cancel each other out because they're the same. The pressure we're going to assume is the same. And you start at 0. So what you want to know is H1 minus H2, or the other way around. Let's write it the other way around. H2 minus H1 is going to equal the starting velocity here, V1 squared over 2g. So if you work through this, you should get this. And if you do that, and if you go back and calculate what V is from this expression right here, which I didn't show it, but it's 56.6, you square that and divide that by 2 times gravity, you get 163 meters is its maximum height. Now quickly, that's the last problem. And quickly I'm going to go through the questions that need to be answered. Quickly I'm going to go through the questions that need to be answered. And these questions are on pages 424 and 425. The first question is number 23. It says, when paddling a canoe upstream, it's wisest to travel near the shore. But downstream, it's best to stay in the middle. Explain why. Well, if you look in the book, you'll see that with laminar flow, the slowest current or the slowest flow is nearest to the walls of the tube, or in this case, the banks of the river. And the fastest flow is in the middle of the channel. When you're going downstream, you want to be in the fastest flow in the middle, and you're going upstream, you want to be in the slowest flow, which is near the bank. Number 24 says, why does the flow decrease in your shower when someone flushes the toilet? Well, that doesn't happen in everybody's house. It depends on if the water is in the same circuit or the same piping system. But basically, the total available flow is a constant. So when some of that flow is diverted to the toilet, then the velocity from the shower has to decrease. Number 25 was kind of an interesting one. I had to look up some stuff online to find the answer to this. It says plumbing usually includes air-filled tubes near the water faucet. As shown in figure 1227, explain why they are needed and how they work. And these are called air dampers or air cushions. And what they are is something that acts as to relieve pressure in the water line. If you don't have this air tube here, when you shut off the faucet, the flow suddenly stops. And by Bernoulli's equation, if the flow suddenly stops, the pressure goes up very quickly. And so this pressure is then distributed through the pipe. Now, it's not enough to break the pipe, but you'll hear this knocking sound, which is actually called the water hammer. And what this air tube does is it relieves that pressure. As a little bit of the water goes up into the air tube and relieves the pressure and keeps the water hammer effect from happening. You may have been in an older house or another type of situation where you shut the water off quickly. And when you do that, you'll hear a knock or a bang sound, and that's basically the sudden increase of pressure banging against the pipe. Number 32 says, why would you expect the rate of diffusion to increase with temperature? Can you explain, can you give an example such as the fact that you can dissolve sugar more rapidly in hot water? Well, diffusion is based on the kinetic principle of molecular motion, where an increase in temperature causes an increased velocity of motion. And that is the reason why diffusion occurs more quickly. And there are a number of examples of this. If you have perfume or another smelly liquid, or if something smelly is introduced into a room, it spreads much more quickly in a hot room as compared to a cold room. The last question is, how are osmosis and dialysis similar, and how are they different? In both cases, there is a semi-permeable membrane which allows something to pass through it preferentially. Dialysis is the transportation of the solute or molecules other than water, whereas osmosis is the transport of the solvent, which is usually water.